Improve the accuracy of the risk assessment model used in banking to better identify potential financial risks associated with customers and transactions. Inputs: customer data such as demographics, credit history, employment information, and financial assets. This data is essential for creating a comprehensive profile of each customer and understanding their financial situation. Inputs: transaction history encompassing all financial activities, including deposits, withdrawals, transfers, payments, and loan repayments. This data helps assess the customer's spending patterns, financial habits, and potential risk factors. Outputs: risk score representing the likelihood of a customer engaging in risky financial behavior. This score is calculated based on various factors and algorithms, providing a quantitative measure of risk. Outputs: risk category classifying the customer into a specific risk level based on the calculated risk score. This categorization helps banks prioritize resources and allocate appropriate risk management strategies. Steps: data preprocessing involves cleaning and transforming the input data to ensure it's consistent, accurate, and suitable for model training. This includes handling missing values, removing duplicates, and converting data into appropriate formats. Steps: feature engineering transforms raw data into informative features that improve model accuracy. This involves creating new variables or modifying existing ones to capture meaningful insights from the data. For example, creating a feature that represents the ratio of loan amount to income or calculating the frequency of transactions. Steps: model training involves using the preprocessed data and engineered features to build a predictive model capable of accurately assessing risk. This involves selecting a suitable machine learning algorithm, such as logistic regression, decision trees, or neural networks, and training it on the available data. Steps: model evaluation involves assessing the trained model's performance on unseen data to ensure its accuracy, reliability, and ability to generalize to new situations. This includes using metrics like accuracy, precision, recall, and F1 score to measure the model's effectiveness. Fine-tune parameters. Regularization parameter controls the complexity of the model, preventing overfitting to the training data and improving its ability to generalize to unseen data. By adjusting this parameter, you can strike a balance between model complexity and generalization ability. Fine-tune parameters. Learning rate determines the step size taken during model training, affecting how quickly the model converges to an optimal solution. A higher learning rate can lead to faster convergence but may miss the optimal solution, while a lower learning rate can take longer but may find a more accurate solution. Metrics. Accuracy measures the overall proportion of correctly classified cases, representing the model's ability to correctly predict risk. A high accuracy indicates a model that effectively distinguishes between high risk and low risk customers. Metrics. Precision measures the proportion of true positive cases among all positive predictions, indicating the model's ability to avoid false positives. A high precision implies that the model is more likely to correctly identify high-risk customers, minimizing unnecessary interventions. Metrics. Recall measures the proportion of true positive cases among all actual positive cases, indicating the model's ability to identify all high-risk customers. A high recall implies that the model is less likely to miss high-risk customers, ensuring comprehensive risk management. Visualization plots. ROC curve plots the true positive rate sensitivity against the false positive rate 1 specificity for different classification thresholds. This visualization helps assess the trade-off between sensitivity and specificity and determine the optimal threshold for identifying high-risk customers. Visualization plots. Precision recall curve plots precision against recall for different classification thresholds. This visualization helps understand the model's ability to balance precision and recall, revealing the trade-off between minimizing false positives and maximizing the identification of true positives. Error analysis. Analyze misclassified cases by examining the characteristics and features of customers that were incorrectly classified as high risk or low risk. This analysis can reveal patterns or biases in the data and identify areas where the model needs improvement. Error analysis. Identify feature importance by analyzing the relative contributions of different features to the model's predictions. This helps understand which features are most influential in determining risk and informs decisions about data collection and feature engineering. Challenges and fixes. Data imbalance refers to an uneven distribution of classes in the training data, where one class, e.g., high-risk customers, is significantly less represented than the other. This imbalance can lead to biased models that favor the majority class. Use oversampling or undersampling techniques to address data imbalance. Oversampling duplicates instances of the minority class, while undersampling removes instances of the majority class, creating a more balanced dataset. Challenges and fixes. Missing data is a common issue in real-world datasets, where certain attributes or features may be missing for some customers. This can hinder model training and performance. Impute missing values by using various techniques, such as replacing them with the mean, median, or mode of the corresponding feature, or predicting missing values based on other features. Challenges and fixes. Feature selection aims to identify the most relevant and informative features for the model. Selecting irrelevant or redundant features can negatively impact model performance and interpretability. Use feature selection algorithms to identify the most relevant features for the model, such as univariate feature selection, recursive feature elimination, or feature importance ranking based on model coefficients. Challenges and fixes. Model interpretability refers to the ability to understand the model's decision-making process and explain its predictions. Lack of interpretability can hinder trust and transparency in the model's output. Use explainable AI techniques, such as rule-based models, decision trees, or feature attribution methods, to provide insights into the model's predictions and understand the underlying logic behind its decisions. Challenges and fixes. Model explainability aims to provide insights into the model's underlying mechanism and how it arrives at its predictions. This helps understand the model's behavior and build trust in its output. Use model-agnostic methods, such as LIME local interpretable model agnostic explanations or Shapez-Hapley additive explanations, to provide local explanations for individual predictions and understand the influence of specific features. Challenges and fixes. Model robustness refers to the model's ability to maintain its performance when faced with noisy data or adversarial attacks. Robust models are more reliable and less prone to errors in real-world scenarios. Use adversarial training techniques to expose the model to perturbed or adversarial data during training, forcing it to learn more robust representations and improve its resilience to noise and attacks.